Solutions to systems of equations. So we're going to start talking about situations where we have two equations happening at the same time. And we're looking for one ordered pair, one situation where both of those equations will be true at the same time. So instead of looking for one ordered pair that makes an equation true, and there's an infinite amount of ordered pairs that make an equation with two variables in it true, we're going to look for that one ordered pair that makes them both true at the same time. So two equations form a system of equations. The ordered pair that is a solution to both equations is the solution to the system. So we'll be calling that the solution, that ordered pair that makes them both true. So what does this look like if we look at a graph? So if I have a graph and I have two equations graphed on that coordinate plane, if they cross in one spot, we have one solution. We have one ordered pair that makes both of those equations true at the same time. So if I was looking at a table for each of these equations, I would see one ordered pair that is on both tables. Now we call that system of solutions, we say it's consistent, and we say it's independent. It's consistent because it has a solution, and it's independent because these two lines are not the same as each other. They're independent of each other. They don't work together. So this is one thing that we could possibly see when we're looking at solving systems of equations. What else could we see? We could see that when we graph the two equations, they actually end up being the same equation. So I have two equations, they look different from each other, but if I go to make a table to graph them, I realize that all of the ordered pairs on one table are the same as the ordered pairs on the other table. If I put them both into slope-intercept form, I realize that they both have the same y-intercept and they both have the same slope. So when I go to graph them, I've got one line on my coordinate plane. Since we do have solutions to this system of equations, pretty much all of them, so we say there's an infinite amount of solutions, infinitely many. We say it's consistent because there are solutions, but we say it's dependent because they're the same line. So one line kind of depends on the other. Whatever is the solution for one also is the solution for the other. So consistent, we definitely have solutions. Independent if the two lines are different from each other. Dependent if the lines are the same as each other. They're the same line. We could also have two equations that never will work together, like when we have parallel lines graphed. So these two lines will never intersect anywhere, so there is no solution to them. Since there's no solution, we call it inconsistent. And if it's inconsistent and there's no solution, we can't really talk about the independent and the dependent. So we still have our three possibilities of solutions when we're solving this. We could have one solution, which will probably happen most of the time. We could have two equations that are the same, and we say there's infinitely many solutions. And it could be inconsistent. There's no solution. We have two lines that never run into each other. So if I have no solution, we say it's inconsistent and we're done. If I do have solutions for this, then I say it's consistent. And depending on what kind of solutions, if I have one solution, I say it's independent. If I have infinitely many solutions, I say it is dependent. So let's look at a couple of graphs and see what we come up with for solutions. So use the graph to determine whether each system is consistent or inconsistent, and if it is dependent or independent. So when I look at this graph here, I've actually got three on this particular one, but we can still work with it with three. You can actually have systems of equations that have more than two equations in them. But I noticed that these lines are all independent of each other, but they do cross in one spot. So these two lines cross in one spot, so we say they are consistent because I have a solution. And since they're not the same line, I say that they are independent. So one way we could see our solutions for systems of equations. Next, I could see two lines that are parallel to each other, and notice both of these lines are in slope-intercept form. They have different y-intercepts, yet they have the same slope. So the same slopes give us two parallel lines. Since I don't have a solution, it's inconsistent, and I can't really talk about dependent or independent since there are no solutions for them. So this one is inconsistent. I would say no solution if I was solving this one. And my last graph here on a coordinate plane, I have one line. Now you'll notice I have two different equations. So when I was going to work with this system, I went, oh, I have two equations. Great, let's see what my solution is. But once I put them on a graph, I realized that they're actually the same line. So if I was making a table, I would realize that the two tables have all the same ordered pairs. And I realized that every solution that works in one also works in the other. It's not any ordered pair, I just can't pick one randomly, but any ordered pair that works in one also works in the other. So since we do have solutions, we say consistent, but since the two lines are really the same line, just kind of disguised in different forms here, we say it is dependent. So for this chapter, we'll be looking at solving systems of equations, and we'll see one of these three situations turn up. We'll see that we have one solution. We'll see that we have we'll see that we have no solution, or we'll see that we have infinitely many solutions.